acid-base titrations. All right, when we're looking at the titration, just like you're doing for redox, we're going to be using a titrant with an analyte and figuring out where the equivalence point is. When we graph this, we call this a titration curve, and its pH is a function of the volume of the titrant added. We're looking for specifically the equivalence point can be found in the curve, and we're looking at where the number of moles of the titrant is equal to the moles of the analyte. So titrant being the known solution, the analyte being the unknown solution in most cases. And it's that same stoichiometric equation that we used when we did redox retitrations. The difference is when we're looking at titration curves, if it's a strong acid base, it's going to look different than a strong base acid. And then obviously when we start adding in weak to weak or strong to weak, we're going to have slight differences in what the curve looks like. Strong acid with strong base, it's always going to have this general shape, where the initial pH is determined by just the concentration of the analyte itself. So whatever is in our Erlenmeyer flask, and it is going to have, in this case, it's a strong acid, so it's going to have a very low pH. As we add in our titrant, in this case a strong base, the pH is going to slowly increase and then rapidly increase at the equivalence point. The equivalence point for strong with strong is always going to be at 7, and if you look at that long line going vertically, let's go back, jumped ahead. Our long line going vertically, it's about halfway, okay? And then we have where our strong base takes over, the pH rapidly, slowly raises to the pH of the solution of the base. Now, if we were looking at this and it was a strong base, weak acid, it would look the same, but the lines would be reversed. We have this straighter line here, straight up, and we go like straight down. The equivalence point would still end up being the same. When we have weak, we're going to have slightly different, okay? As you can see, we're not having that straight curve going up. We start at an initial pH, it's going to be higher, so it's going to be closer to 7. And you're going to use the Ka value to determine the pH. And then also notice that the steeper line, there's this steeper line because at this point the weak acid is acting as a buffer and it's resisting the change in pH until it's overwhelmed and our strong base takes over. Halfway to the equivalence point, we have pKa equaling pH. So if we look at it and we go kind of halfway, so 25 here, this is where pKa equals pH. So our pKa or our pH is going to be about, let's say 4.8. So that is also the pKa. And you can obviously determine that mathematically, or in this case, you can give an estimate. So it's going to be based on the concentration of the conjugate of the weak acid or base. So if our weak acid is hydrofluoric, like we saw in the previous, it is going to be based upon our conjugate base, okay? And then at the equivalence point, obviously, is still where molarity, molar ratios are equal, so the mole of our acid is equal to the moles of our base. But in this case, you should look at it, you should see that it is a higher equivalence point. It's not going to be at 7, it is going to be more basic, because if you look at it, it is based upon our concentration of our weak base, of our conjugate acid. And then finally, once there is more sodium hydroxide or our strong base versus our weak acid, the pH is going to be based upon our strong base. Now, if we started with a weak base, strong acid, we would take that reaction and just reverse it. start off with our subtle curve change, and it would be closer, again, it wouldn't be as high as 12, it would be a little closer to 10. And we'd have more of a curve going down, and then we would have a straight line, and then it comes across. And again, our equivalence point, notice it's not going to be at 7, it's going to be below 7 if it is a weak base with a strong acid. Finally, we have polyprotic acids. These are really interesting. Polyprotics are ones that have multiple hydrogen ions that they could share. So you can see that there's going to be multiple equivalence points. We have equivalence point where it gives up all of the first hydrogen, it becomes H2PO3, and then we have our second equivalence point where H2PO3 becomes HPO3. Okay, the acid species could be determined in each region. It's always just one less. pKa is still going to be halfway to the equivalence point, and there's going to be multiple equivalence points. (8.6) molecular structure of acids and bases. So it's mostly focused on the structure of acids. Stronger acids are going to have the weaker HX bond. It's actually why hydrochloric is a stronger acid than hydrofluoric. Hydrofluoric has a really strong bond with hydrogen. So it's not going to be as strong of an acid because that hydrogen is not going to be pulled off as easily. Oxyacids have an atom bonded to oxygen, usually with hydrogens attached to it. So usually we're thinking about something like sulfuric acid, where H2SO3, and it's going to look something like this. Okay, so it has these oxygens that are more electronegative. They're more polarizable. The more positive that the H will be, and more they could be pulled off from the acid, because what's happening is this oxygen is going to be pulling on the electron on this hydrogen. So this hydrogen becomes more positive, and it could be more easily pulled away. And it also means that this conjugate base is going to be more stable because it has all of these oxygens that are keeping tight to those electrons. So strong acids are more polarizable. They have a lower bond strength, so they have a low enthalpy, and they're really stable conjugate bases. And so those are the three things that contribute to being a strong acid. Weak acids are going to definitely not have as much of a dipole event. They're not going to be as polar. There's less oxygens to stabilize that conjugate base. And so a really common weak acid that we deal with are carboxylic acids. pH and the pKa. So we can actually look at how pH and the pKa are looking compared to one another in a acid-base titration. So when the pH is less than the pKa, the acid form of the ion has a larger concentration. Essentially, it's going to be the acid in higher concentration, the conjugate base is going to be in lower concentration. And then due to common ion effect, the acid's going to precipitate out. When the pH is greater than pKa, the base is going to have a larger concentration than the acid. Pretty straightforward. And then we could use indicators. You should be familiar with these in previous tritations we talked about with redox. And we're just looking at a color change based upon exposure to an acid or a base, or how much hydroxide hydronium are in solution. Each indicator has an effective pH range, like phenolphthalein will turn pink. You guys use that. And it only turns pink with a pH between 8 and 10. Methyl red, it's going to turn yellow-orange with a pH of 4 to 6. So it's going to be great when we have lower, looking at for an acid instead of looking for the base. And there are so many different varieties of indicators that we can use that will be effective for whatever titration that we want to do. Just know when we talk about endpoint and equivalence point, and it should be clear by looking at the phenolphthalein endpoint pH versus the equivalence point. Equivalence point and endpoint should have similar values in the end, But the equivalence point is when the titrant of moles are neutralized with the unknown moles of whatever. So essentially the acid and the base neutralize each other. Endpoint is when that indicator undergoes a color change. So in our case, it would be slightly past the endpoint in most of the times. (8.8) Properties of buffers. As we talked about previously, buffers resist change in pH. Now, the resisting changes only happen in small amounts because the more acid or base, the more likely we're going to overwhelm the equilibrium of our buffer. So essentially, a buffer solution takes advantage of the common ion effect of an equilibrium solution. So we create put our acid and a salt with our common ion in the same solution at specific values, and we end up with a buffer. If our acid is added, it's going to react with our conjugate base to reduce the change, and if our base is added, it's going to react with our conjugate acid to reduce the change. So for example, our hydrofluoric acid is our buffer, and again you could use sodium fluoride as our common ion that we would create this buffer solution. If the base was added to it, the solution would react with the H+ in the acid to form water, and so we have this water being formed, and it removes the hydroxide, and so now it's going to be keeping the pH low. If an acid's added, the fluorine ion is going to react with the acid, with the hydrogenium, and we're going to again keep the pH higher instead of reducing it from the acid being added. Hasselbalch equation. Now don't get mad at me for not giving this earlier, but I wanted you to make sure you could understand how to use an ice table before we started using the shortcut here. So when we're calculating the pH of a buffer, we can actually use the Henderson-Hasselbalch equation, and this is just the algebraic breakdown of how Henderson-Hasselbalch was created. If you want to look through it and understand it, ask me questions about it, that's fine, but essentially what we get down to is the pH is equal to the pKa plus the log of the concentration of the base divided by the concentration of the acid. And so you can use this to find the pH of a buffer. Not equilibrium, not anything else. This is only for the pH of a buffer. So what is the pH of a buffer? That is 0.12 molar lactic acid and 0.1 molar sodium lactate, the lactate being the common ion. And the lactic acid's Ka value is 1.4 times 10 to the -4th. So we need to use our Henderson-Hasselbalch. So that is pH is equal to the pKa plus the log of the base concentration over the acid concentration. So we know Ka, so we can actually figure out the pKa would be the negative log of 1.4 times 10 to the -4th, so it should be just a little bit less than 4, somewhere around 3, and we do find it to be 3.77. And then we plug everything in. So pH is equal to this is 3.85. I jumped ahead and looked at the wrong answer. So 3.85 plus the log of our base, which is the lactate, sodium lactate, 0.10, over our lactic acid, 0.12. And we get a negative point something here, and we end up with 3.77 as the pH. And it's that straightforward. It's 8.10 buffer capacity. So a buffer can have a specific amount of ability to prevent pH change. The greater the concentration, the more it can buffer the solution. You can create a buffer solution that is specifically geared towards buffering an acid or a base, and all you have to do is make sure that you have a greater concentration of the conjugate acid over the base to create a buffer capacity for a base over an acid, if that makes sense. So if you want to buffer an acid more than you would buffer a base, you're going to make sure that you have a greater concentration of the conjugate base in your buffer. All right, so practicing. Let's look at this equation or this problem here. We have a buffer is made by adding 0.3 moles of our acid and 0.3 moles of our base into a 1 liter solution. The buffer of the pH of the buffer is 4.74. So remember that buffer pH is equal to pKa. Okay, so we can actually know what the pKa is based upon that. So we add 5 milliliters of our sodium hydroxide. So what we need to do is figure out what the pH is going to be after adding 5 milliliters. So we have to start with a dilution. So remember, if we have 0.3 moles per 1 liter, it's 3 molarities, okay? So we're going to dilute or see our dilution 1 liter, right, of our, this is going to do the acid. And our new volume is 1.005 because we added 5 milliliters. So 1 liter plus 5 milliliters is 1.005 liters. And what's our new concentration? 2.786. Oh, nope, sorry. Let's go back. 2.985, sorry. 2.985. And then we look at it and we're still adding 3 moles of our base too. So it's actually the same exact dilution. So our concentrations of our acids and our base are equal, which is generally what we would see in a buffer anyway. We're going to figure out the dilution of our sodium hydroxide. So we have 4 molarity, and we have 5 milliliters of it, which really, if we write it correctly, would be 0.005 liters. And we're going to dilute it into 1 liter. So we have 1.005 liters, and what is our new molarity? It is 0.0199. Okay, so because we're adding a base, that means it's going to react with the acid. So the acid is going to decrease in concentration because it is reacting with the base, the strong base. So we take our acid concentration, subtract our sodium hydroxide concentration, and we end up with 0.2786. And because we're doing that, that means our conjugate base increases, so we're going to add 0.199 to that, and we end up with 0.3184, and that's for our base. And we assume all of the sodium hydroxide has been used up. So then we can just say pH is equal to pKa, which is 4.74, plus the log of our base over our acid, and we get an answer. Now, we should expect it to increase because we're adding more base. So when we do our math, we get 4.80. All right, so that's how to calculate with a buffer. Well, let's look at it. Let's compare that value. So let's say, let's put the pH here, 4.84. Oh, sorry, 80. All right, so let's compare that to how much our pH would change if we added the same amount of sodium hydroxide to pure water. So again, it's dilution. We have 5 milliliters of 4 molar. We dilute it with a liter. We have our new concentration. Which we've already figured out, right? It's 0.0199. And because we're just adding hydroxide, we don't have to do anything else. We can actually define the pOH with the negative log of 0.0199. And we end up with 1.7. That's the pH. pOH, we have to find the pH, so it's 14 minus the pH, and we get 12.30. So you can see how much a buffer can affect our pH change, or actually prevent the pH change, because this is only 0.3 moles of a buffer, really. So for the very small amount of buffer, we can have a very large effect on how much it can prevent our pH from changing.